Welcome to This Explainer. Today, we're diving straight into real chemistry exam questions from the MDCAT to completely demystify the foundational rules that govern matter itself. Whether you're prepping for the big test or you're just kind of fascinated by how the universe is stitched together at a microscopic level, these questions, they're your skeleton key. And we're not just going to give you the answers. We're actually going to break down the mechanics behind every single one. Let's get into it. Okay, here's our roadmap for today. We're structurally breaking these questions down into 5 core pillars. 1. Anatomy of the atom. 2. Decoding periodic trends. 3. The mechanics of reactions. 4. Oxidation and electrons. And finally, 5. Forces that bind us. Section 1. Anatomy of the atom. Architectural structure. All right, here is our first puzzle from the source material. It challenges us to identify the specific orbital hybridization of sulfur tetrafluoride, or SF4. The options range from sp squared all the way to sp3d squared. Now, to the untrained eye, sure, this just looks like alphabet soup. But it's actually this beautifully precise way of describing how an atom physically shapes its own personal space just to bond with other atoms. Now, what's really fascinating here is how atoms literally shuffle their electron clouds around to make room for new bonds. Hybridization isn't just some abstract theory on a chalkboard, you know? It's the actual physical and mathematical mixing of standard atomic orbitals. Basically, the atom takes its s, its p, and sometimes its d orbitals and merges them to form entirely new identical hybrid orbitals. Why? So it can pair up its electrons and connect perfectly with its neighbors. So let's apply this to our molecule sulfur tetrafluoride. Sulfur sets in group 16 on the periodic table, right? That means it has 6 valence electrons. It uses 4 of those to form bonds with the 4 fluorine atoms. That leaves 2 electrons left over, which make up 1 non-bonding lone pair. So 4 bonds plus 1 lone pair gives us a total of 5 electron domains. And because it has 5 domains, the central atom literally has to use 5 mixed orbitals, 1 s, 3 p's, and 1 d. Put that all together, and you get sp3d hybridization. That makes option C the undisputed answer here. Moving on to section 2, decoding periodic trends, analyzing elements. This next question really requires us to visualize ions, not just as letters on a page, but as actual physical spheres that expand and contract. We need to determine which of these 4 ions, sodium, magnesium, fluoride, or oxide, takes up the most physical space, meaning which one has the largest ionic radius. Here's the trick. Every single one of these ions has exactly 10 electrons. They're what we call isoelectronic. But their nuclei, totally different story. Let's compare the oxygen ion, O2-, to the magnesium ion, Mg2+. Magnesium has 12 positive protons in its nucleus, pulling inward on those 10 electrons. It acts like a super strong magnet, pulling that electron cloud in nice and tight. Oxygen, on the other hand, only has 8 protons pulling on those exact same 10 electrons. So the crucial takeaway here is that fewer protons pulling on the same number of electrons leaves the electron cloud looser and far more expanded. That gives O2- the largest ionic radius, making option D our answer. Staying with periodic trends, this next question asks which of these elements fights the absolute hardest to keep its first electron: sodium, magnesium, aluminum, or silicon. Remember, ionization energy is exactly that. It's the sheer amount of energy required to rip an electron away from a neutral atom. If you picture the periodic table, these 4 elements are all sitting right next to each other in period 3, reading left to right. Now, elements on the far left, like sodium, are basically eager to lose that one outer electron just to achieve stability. But as you move to the right across the period, the positive charge of the nucleus increases without adding any new electron shells, so it's pulling everything in tighter. Because ionization energy increases as we move across the period, silicon, which sits furthest to the right out of these choices, requires way more energy to lose an electron. That makes D the correct choice. Next up, section 3, the mechanics of reactions, catalyst statements. You know, catalysts literally run the industrial world. From refining petroleum to the enzymes that are digesting food in your stomach right now, they are absolutely essential. But how do they actually work? This multiple choice question tests exactly how they manipulate chemical reactions. Do they increase energy? Do they change the equilibrium? Let's take a closer look at the options. Think of a catalyst like a tunnel going through a huge mountain. Normally, if reactants want to become products, they have to hike all the way up and over the peak. That huge physical effort is the activation energy. Now, a catalyst doesn't lower the mountain itself, and it doesn't change your starting point or your destination. Instead, it just provides a completely different, lower energy alternative pathway. It's the tunnel. This means products can form much faster without the catalyst itself ever being consumed in the process. And that points us directly to option C. Applying reaction mechanics to our next question from the source material, we look at a classic acid-carbonate reaction. When dilute hydrochloric acid reacts with sodium carbonate, there's a very predictable chemical swap that happens. The reaction produces sodium chloride, water, and crucially, it effervesces. It bubbles. And those bubbles are carbon dioxide gas being rapidly produced. So, carbon dioxide is the undisputed correct answer for that chemical interaction. All right, section 4, oxidation and electrons, nitrogen and HNO3. To solve this question about nitric acid, or HNO3, we basically have to turn a complex molecule into a simple math equation. We're being asked to find the exact oxidation state of the nitrogen atom that's trapped right in the middle of this molecule. Now, what's really interesting here is how visually mapping the known charges makes the missing piece just reveal itself. We know hydrogen almost always has an oxidation state of +1, and we know oxygen is almost always -2. Since there are 3 oxygens, they contribute a total of -6. But the entire HNO3 molecule is neutral, meaning all these numbers have to perfectly add up to 0. So +1 from hydrogen plus our unknown nitrogen -6 from the oxygens equals 0. That simple algebra forces nitrogen to balance the scale at +5. That makes option B the correct choice. Finally, section 5, forces that bind us, intermolecular forces. This final question tests your hierarchy of molecular attraction. It's asking, out of the 4 options presented, London dispersion, dipole-dipole, hydrogen bonding, and ion dipole, which force holds matter together the absolute tightest? Let's stack them up. Down at the bottom, you have London dispersion forces. These are just temporary, fleeting attractions found in all molecules. Moving up a step, you have dipole-dipole forces between polar molecules. Stronger still is hydrogen bonding, which is kind of like a supercharged version of dipole-dipole. But at the very top, this brilliantly illustrates the hierarchy of power, showing that the interaction between a fully charged physical ion and the partial charge of a polar molecule, the ion-dipole force, is definitively the strongest. I mean, this is literally the force that allows water to rip solid salt crystals apart. So that makes option D the correct answer. As we wrap up this explainer, we've seen exactly how electrons dictate structure, how protons dictate pull, and how molecular math literally drives reality. So I want to leave you with a question to ponder. If these unseen, deeply foundational chemical forces shape the reality you interact with every single day, from the water you drink to the tech you use, how does mastering them change the way you view the physical world around you? Keep questioning, keep learning, and thanks so much for joining me on this.